Okay, YouTube, in this video we're going to be looking at is summation notation. And the root here is exactly what you would surmise it would be, is the word sum. Okay, so when we talk about summation notation, what we're really looking at is like addition notation is what this really is. And what we're looking at is addition of basically very predictable things along the lines of some rule. So we're going to look at this notation here in a second, but essentially if we were to have something just as an example, so e.g. as an example here, let's let there be a rule an and it's equal to 2n. If we were to write out the terms of this sequence, of course the first term, if we plug in a1 here, would be 2 times 1, we get 2. Next term would be a 4, and then a 6, and then an 8, and this would continue on and so forth. What I can say is that there will be some times in which we'd be interested in adding up, say, the first however many terms of a sequence. And when we do this, it looks like this instead here. What we end up with is just this sum that can extend as long as we want it. But I would say if I were to add up the first 4 terms, I would write it this way. If I were to add up the first, I'd say 400 terms, what I'm going to be telling you is that it becomes a little bit difficult to write sums that large in that fashion. So what we're going to do is we're going to come up with a new way of writing sums that can be very, very large, but predictable sums that I could say that there exists a rule for. So looking at this, we say the sum of the first however many terms, so we say n terms of a sequence is represented by the summation notation thusly. So when you look at this right here, this is indeed summation notation. So in terms of what we see here, this is the capital letter sigma. So the capital letter sigma, okay, we use the word sigma, or the letter sigma is used, let's put it that way, to indicate that there is a sum. Sum and sigma kind of start with the same letter there, so we use the sigma. We would say that this capital sigma here, really what it's indicating is we're going to be adding together the terms of this sequence right here. So when you look at AI, the first thing I want to admit here is that this is the rule. This is the equivalent of saying that this rule right here would tell you what the terms of the sequence are. But using this rule, what we're going to say is I want to add up the terms of this sequence starting at 1 and going up to n. So with respect to what this 1 and this n indicate, we're going to call this the lower limit of summation, and that is what this is right here. Excuse me, and what it represents is the starting term. So I'm going to write this here. The starting term, the term that I want you to start adding at. And this top value here is the upper limit of summation, and we would say that this is the last term in the sum. Last term in the sum. So really what you see here on the right, excuse me, is the sum of the first term through the nth term of this rule a subscript I. And you'll notice that we use an I here. Now I've kind of covered it up. But basically what this indicates is starting at the first term, we're going to add up the first term plus the second term, third term, so on and so forth, and we're going to stop at the nth term of this thing. And so another way to write this sum of, say, 400 terms right here might be conveniently to just say, well, I've got the rule, and the rule is 2 times n. Now I'm going to switch this over to I for the purposes of this video. And I do not mean I is equal to the square root of -1. I don't mean it in this case. I mean I is just some letter. You'll notice that here this note says any letter can be used for the index of summation, which is what we call that I. We could use I, J, and K, and basically this says that those are used commonly. So what we could say is the sum of the first 400 terms of this, if I wanted to write it conveniently, is I would just basically say that, hey, you know what, add up starting at the first term, going out to the 400th term, all of the terms of the sequence here. And you know what, a person could go plug in 1 through 400 and find all the terms of that sequence, but that's essentially what it means. So we write here, when we write out a sum that is given in summation notation, we are expanding the summation notation. So example 5, which I mentioned here, showing how to do this. Let's take a look at example number 5. And in example number 5 here, essentially what we're going to be given are these sums. And what we want to go do is go and expand them. So before we expand them, let's go ahead and interpret at what these things are asking us to do. So starting with letter A here, it says, let's go find this sum. Now, how would I read this? I would read this as the sum from 1 to 6 of 2i squared. You know, that's pretty technical though. You know, the sum from 1 to 6 of 2i squared. We could also say this, the sum of 2i squared starting at the first term and going out to the 6th term. Stopping at the 6th term. That's a little bit more plain English, okay? So that's essentially what we're going to do here. And if we're going to expand this sum, essentially what we need to do is admit, and I'll write this just for this first example, what we're doing is finding a1 and adding it to a2, and adding that to A3 and A4 and A5 and A6. So what this means is we're going to need to know the values of A1 through A6, meaning that we're going to have to plug it into our rule. So what I'm going to say here is to expand this, we would really just say this. We'd say A1, which is really 2 times 1 squared. Plus now, we would say A2, this is not a fraction, I'm saying this is the second term. I would get 2 times, in this case, 2 squared. So I'm going to go ahead and continue this sum. We would have 2 times 3 squared plus 2 times, I can keep this up I suppose, 4 squared, 2 times 5 squared, and I know I'm running out of room here, but we say 2 times 6 squared. And this would be our expanded sum. So all we have left to do here is go ahead and simplify this, starting with doing our exponents first here. We have 2 times 1, which is 2, plus 2 times 2 squared. Now 2 squared is 4, so 2 times 4 is 8. Here we get 2 times 9, so we get 18. Here we get 2 times 16, which is 32. 2 times 25 is 50, and 2 times 36 is 72. So we would need to add all of these together, and I'm just going to grab an easy calculator to work with here. Should use a graphing calculator, see if this opens up here, but I'm going to use this guy instead. So if we were to take this now, we say, okay, so 2 plus 8, that's 10, plus 18, plus 32, plus 50, and plus our 72. What we get is a total sum of 182. So now, what I'm going to do is I'm going to come up here, I'm going to say this sum right here equals 182, and yes, I kind of cut off the 6 there. But what I'm going to say is this, all of this adds up to be 182. You can see how that gets quite extensive even after adding up 6 terms. So we're going to learn some tricks here to add these up more easily, but let's go ahead and take a look at these other two sequences that you see here. So this one's different, and what I want you to notice is that this first one said add up the first through the 6th term of this sequence defined by this rule. In this instance, what we're going to see here is this, if I block this off, we're adding up only the 3rd through the 5th term of this. So above this, what I'm going to write is this, we're adding up A3 plus A4 plus A5. That's what this sum really is asking us to do, where this is our A, and I'm going to write K. Notice that we're using a K this time for our index of summation. So to write this out in expanded form, we would just simply write, well, 2 to the 3rd power minus 3 times, plus, I'm thinking about multiplication here, 2 to the 4th power minus 3 plus, we'd have 2 to the 5th power minus 3. And you can see that we found our 3rd term, 4th term, and 5th term. So again, we're just going to simplify this. And so we get 2 cubed minus 3, which is 8 minus 3. So 8 minus 3 here. Here we get 16 minus 3, and here we get 32 minus 3. But essentially 8 minus 3 is going to give us a 5 here. So 5 plus now 16 minus 3 is 13, plus now 32 minus 3 is 29. So adding these together, again, we get our calculators ready here. But we could say, clearing this out, we get 5 plus 13 plus 29. So 47. So we would say that this sum right here, the whole thing comes out to be a sum of 47. So for this last one here, it's not going to take long to write. The interesting thing is, and we want to highlight this here, we say the rule is a constant. And whenever you get a rule that is a constant, really what that means is when you plug in, say, A1 here, if we want to find A1, it's just 4. And A2, it's just going to be 4. And A3, it's just going to be 4. In other words, if there is no I here in this case to plug in I in for, then really you always get 4. So the interesting thing is we're really going to get for our first term here 4, plus our second term 4, plus third 4, fourth term is 4, fifth term is 4. So we really get 5 4s here, and so that ends up coming out to be a sum of 20 here. Excuse me. So for this last little bit here, what we're going to do is kind of the opposite. We learn to read this summation notation as starting here and ending here, go add up all the terms of a sequence defined by this rule. What I want to do for this second part is this, express each sum using summation notation. So is it possible for us to write a sum here, like this, for each of these things that would express the sum that's indicated for each of these patterns? So looking at what we have here, let's go ahead and just start with this. I look at this, I get 1 squared, 2 squared, 3 squared, so on and so forth. I could almost see here that if our domain, these are a n values here, this is my first term, this is my second term, third term, this would be like my 9th term out here. So what I'm going to look at here is that I'm going to use an I on this one. We're going to start at the first term here. So we have our first term, and we're ending at our 9th term. So first term to ninth term, let's go ahead and put our lower and upper limits on our sum. So now for our rule, what we need here for a rule is something that would define, if I knew the term number, how would I get the term value? And it looks like all we're really doing is taking the term number and squaring it. And so I would say that this is just an I squared as our rule here. And that would be the sum that would basically say the sum of the first 9 terms of i's squared. Excuse me. When we look at something like number or letter B here, we would say it looks like, again, we might be starting at our first term. We could look at this as being a fraction over 1. But you'll notice that the top of this rule is always 1. And as our term number grows each time, our first term has a bottom number of 1. Our second term has a denominator value of 2. Basically, whatever the term number is, that's what the denominator is equal to. So we could say the rule here is kind of like 1 over n. But you notice here that we've got this over here. Actually, no, not 1 over n. Apologies. This is not 1 over n because we can see that our third term here is not 1 over 3. I got a little hasty there. 1 over 4, 1 over 8. I guess what we can notice here is that this is powers of 2. We're multiplying by 2 every time. So in that case, what we're going to say is this is very exponential. The only reason I say that is because they kind of give us the rule right here. So we're going to say that the nth term really is 1 over 2 to the n minus 1. And it looks like we're starting at let me go back and change this to an I. I want to say I because what we're going to do here is this. We're going to say that I starts at 1, but then stops at the nth term is what the last term we plugged in was. And I'll leave that in blue there. But this is our sum right here for this particular series. Cheers.